Okay, we're moving into moisture or humidity, saturation, stability, all mixed together as part of moisture. Moisture is just water in the air. So that's what we're going to talk about this week. See what we can figure out with that a little bit. So, how does the water cycling impact Earth's atmosphere? We talked about the hydrosphere as being a water interface with the Earth. Well, here is an example of an atmospheric river. Literally, it grabs moisture across the Pacific in this case and pulls it into the northwestern U.S. And you can see the cloud band here going all the way across the Pacific. And this can really dump a lot of rain in the western United States. Sometimes these cloud bands will be a little further south and they'll come into Southern California, sometimes Northern California. And when Southern California doesn't get one of these, it can really lead to a very dry winter. But by the same token, when they get them, there can be tens of inches of rain in the mountains, and sometimes that can translate into more than 10 feet of snow in some locations. So with that, what is the total amount of water? It's almost all confined to the lower part of the troposphere. And if all the water vapor were removed, you'd basically be getting about an inch of rain everywhere in the world. So that's really not a lot of moisture in the overall scheme of things. Here is an example of the water cycle. Water evaporates from the ocean or maybe a lake, and it can condense back into clouds over the same area and drop that same moisture back into the ocean. Just keeps repeating the process. But some of that moisture maybe goes inland, goes over some mountains. Maybe it causes some precipitation on the mountains, such as snow or water coming down on the slopes of the mountain. You get runoff then down into the valley. The bigger the slope, the faster the runoff. So some places that have very steep hills, like parts of West Virginia, are going to have pretty fast runoff down into the lower valleys. So now you wind up with that water down in the valleys, and it eventually is going to evaporate back into the clouds, and the air might move it back out into the ocean for all we know. Or some of it will seep into the ground. And if you have a big city, think about it. You have asphalt everywhere. You're not getting much water getting into the ground that way. It's going onto the roads. A few years ago, when Houston got tremendous rainfall, they wound up with tremendous amounts of water flowing down the roads because it couldn't soak into the ground because it had all this asphalt. And the roads actually are designed in Houston to be a conduit for the water to get it in the drainage system that they have designed. However, when too much rain falls, it gets overflowed and the roads get too deep. And that is what happened with Harvey. So how does water, we know water changes phases. We know it has evaporation, condensation, transpiration when it's coming out of the roots of plants as well, or evapotranspiration, sublimation, deposition. And water is the only element on Earth that can change phase within the atmosphere. So that's one of the key things. Humidity basically describes the amount of water vapor in the air. And it can vary from season to season, from day to day, even within a few minutes of time. Summer, typically more humid. Winter, typically drier. And here are some ways we measure it. Notice there's a whole bunch of them listed here. And you're going to get to see each one of these a little bit anyways in this. So water vapor content, think about water vapor has an air pressure. So it contains a little bit of pressure from that water vapor, just like any gas has pressure. And up to about 4% of the atmospheric mass in the lowest levels can be from water vapor. So some ways we measure that is mixing ratio. It's basically that water vapor mass divided by the mass of dry air in some quantity. 1 foot by 1 foot, 1 meter by 1 meter, whatever. It's just a ratio. A mass of water vapor per kilogram of dry air. Specific humidity just adds the water vapor back into the dry air. So you get a slightly higher value for the bottom number. So typically specific humidity is going to be just a tiny little bit less than mixing ratio. Absolute humidity is the mass of water vapor per unit volume of humid air. So it's the number of grams of water vapor per cubic meter of air. Air becomes saturated. It means at what point is the water vapor both condensing and evaporating at the same rate, so that some of the water vapor is condensing into water droplets, some of the water vapor is going from the water droplets back into the air, evaporating. When they match, that's saturation. So air at some point has a maximum humidity of 100%, and that is saturation. And saturation can be added to all of these terms. Interestingly, when you add heat to water, it increases kinetic energy in the water molecules. So what happens? They easily escape from the water surface and go back into vapor. So the hotter it is, the more water you need to have in order to reach saturation. Vice versa, the colder it is, the less water. And here's just a graph of that saturation. Relative humidity is a term almost all of us hear. We hear, oh, wow, we know the relative humidity is 70% this morning. Well, relative humidity is this vapor pressure over the saturation. So in other words, saturation vapor pressure is how much water vapor that air parcel can hold and lose just a little bit of it into evaporation and a little bit of it into condensation. It reaches that level. Vapor pressure is whatever's actually there. So when they're equal, you're saturated and you're 100%. Now, if you have temperature changes, that's going to change that water vapor. So if the air were to cool, more would have to condense. You'd wind up condensing more out. Even though the relative humidity stayed 100%, more and more water vapor would have to condense out into water droplets, the more and more that air parcel cooled. One of your critical thinking questions is exactly that this week. It talks about 100% saturation and relative humidity, but then you're lifting that air parcel. You lift an air parcel, it is going to cool. That means that some of that water vapor has to condense out. So the amount of water vapor is going to actually diminish, and more of it is going to become liquid. Look at a normal day. The relative humidity is highest in the morning. Why is that? Because in the morning, the temperatures are coldest. They can't hold as much moisture. So the relative humidity, even though the same amount of moisture is there, is going to be higher. By afternoon, temperatures are hotter, can hold more moisture. Relative humidity actually is going to fall. And that is very typical of many days during the year. Dew point is another measure of water vapor. If you cooled the air at no change in pressure, that air will eventually reach saturation. What is that temperature that it took to reach saturation? That's the dew point temperature. It's where dew forms, literally, or frost. And you can see the changes in dew point between the year. Look at how much warmer they are. Some of them are well up into the 40 to 50 temperatures in January, and in July, dew points go up into the 70s, and you'll even see them in the 80s sometimes. So a lot more moisture is held in the water in the summertime than it is in the wintertime. That's why when you get the thunderstorms, you get so much more rain with them. And when this happens, you get condensation when it reaches 100%, and it can produce clouds. So how the heck do we get the moisture to condense? Well, one way is by cooling the air. So you have to have ways of getting the air to rise so it will cool. And when it cools, the saturation vapor pressure drops. The vapor pressure remains the same. You wind up getting get fog or clouds. It can happen at the ground at night. If you have cooling, look in the valleys, the air gets colder and colder in the low valley. All of a sudden you wind up with fog in the bottom of the valley. All right. The atmosphere air parcels can be stable, or they can be unstable, or they can be neutral. This seems to confuse a lot of people, so I'm going to try to explain it. Think about a hot air balloon. You ever watch a hot air balloon go up and up and up? Why does it go up? It's lighter than the surrounding air. So that balloon density, because it's hotter, it continues to rise. The more colder air is denser. So all you're looking for, whether a parcel is stable or unstable, is that air parcel colder or warmer than the surrounding air? And yes, overall, the air is going to have some kind of a cooling process as it goes up. But an air parcel that's being pushed up from the ground might cool faster than the surrounding air, or it might cool slower. If it cools faster, then at some point it's going to be several degrees colder than the surrounding air. It's going to want to sink back down to where it is the same temperature. That air is stable. Unstable means that same air parcel went upwards, but it is not cooling as fast as the surrounding air. So now it is warmer. So what are some ways that this can happen? Well, let's go back here a minute. We talk about temperatures cooling at 9.8 degrees Celsius per 1,000 meters on dry air. Well, we talked also last time that conditional instability is temperatures only dropping about, the moist adiabatic lapse rate is about 6 degrees. So if I have an air that's cooling at 8 degrees Celsius per 1,000 meters, and I lift a parcel of dry air, that parcel of dry air is cooling at 9.8. So at 1,000 meters up, that same parcel of air is now 1.8 degrees colder. If, on the other hand, I lifted a very moist parcel of air right at saturation, it's only going to cool 6 degrees in 1,000 meters. That same air parcel is going to be 2 degrees warmer. So that is going to be that parcel that's unstable. It's warmer than the air next to it. It's going to keep rising. Other things that can cause lift are fronts, cold fronts, warm fronts. They can push an air up. And if they cause lift and the air parcel becomes unstable, not all the time does it become unstable. But if it does, that air parcel is going to want to accelerate even more upwards, going to cool even more rain's going to come out, and you wind up getting thunderstorms many times, very unstable. Mountains can lift an air parcel. And there's something called the lifted condensation level. It's the altitude at which an air parcel, as it's rising, reaches saturation. And it is going to be the base of the clouds. There are rain shadows. If you go over mountains, I'll give you an example in West Virginia. The mountains in West Virginia run north-south, pretty much. Say I have a very strong east wind hitting those mountains. Well, that east wind is being pushed up on the east side of the mountains. It's pouring down the rain. On the west side, that same east wind is beginning to drop down the mountain, down the slope. It's warming, and when it does that, the saturation vapor pressure becomes higher or greater. You're losing saturation, and you may not even get that much rain on the west side of the mountain. The same could happen in the wintertime. You get the cold air coming down off the Great Lakes, hitting the mountains in West Virginia, maybe, and they'll lift up, causing precipitation on the west side of the mountains. And on the east side, sun's coming out. Converging winds around low pressure systems or sea breezes might cause lift. So I just wanted to show you a little bit. Here's today's front. We have a front in Ohio. Look at the current radar. Rain right along that front. There's that lift. One of the interesting things is tracking moisture into a front. Where did it come from? Well, if we looked at the moisture, it's not coming out of the Gulf of Mexico. It's probably actually air that came in off the Pacific, lost a lot of its moisture. That's why there's not much rain here, because it can't find a lot of moisture to work with. Now you look down the Gulf of Mexico, and if you were to go back here, you'll see there's an old front down in the Gulf of Mexico causing lift. And we have lots and lots of moisture down there. causing thunderstorms. Precipitable water is just another way of looking at the total amount of liquid. If you were to condense that water out, and you can actually see right along the intertropical convergence zone, which is right down near just a little bit north or near the equator this time of year, you have lots and lots of moisture. Look at the drier air coming down out of Canada or across from the poles, and you can see the drier air pushing south. All that warm, moist air. Here's the Gulf Stream coming up. You have lots of moisture there. Finally, I just wanted to look at one sounding. We've talked about STUVs, and let's see if we can get this better. All right, here it is. If I lift an air parcel right here, just off the surface, you see this dashed line right here? It's a little hard to follow, but there it goes up. That's the moist adiabatic. So this is the current environment or the lapse rate of all the air around that air parcel. You'll notice that all the way up, I am just a little bit to the right of that air parcel. So I am warmer. I am unstable. That air parcel is going to want to keep rising, and that's why showers and thunderstorms are anticipated down around Miami today. So I hope you got something out of all this. Please don't hesitate to ask if you have any questions.